Okay, so today is our last class before spring break. Okay, so today is 23rd. So, so you have to go for another meet. You already complete the first meet. All of you did well in your first meet. I saw that. Okay, so next we can set our next midterm. So it's after the spring break. Uh, 4 and 6 is your first week class. Okay, so I think, okay, take some time. 13. Okay, 13 I will set your okay second midterm at April 13. Okay, April 13. And okay, of course I'll give an announcement as well. Your second midterm will be April 13. and syllabus will be I think module 4, only module 4 this time. Okay, only module 4. Okay, so please read carefully the PowerPoint that I uploaded. Okay, that I have uploaded. Okay, PowerPoint that I have already uploaded. On, yeah, here is also 30 questions is there. So please read carefully each PowerPoint. Okay, each PowerPoint carefully. Okay. Just 30 questions only from only your processor management as well as thread. Yeah, this kind of stuff. Okay. Okay, process versus thread, this kind of stuff. Okay, if you read carefully, then hopefully you'll get a good score this time. Okay, because it is very small syllabus. Okay. Also, in our last class, we have already started the module 5. We learned the process synchronization as well as the data. This kind of stuff we will start. Already we have started. I showed you one example as well. What is the process synchronization, and in which cases you need the process synchronization. Okay. Okay. Let's start. Let me share my screen. Share my screen about both things. Okay. If you can see my screen. Now, let me turn off my video, then it will be clear for you. Okay, I didn't open the PowerPoint slide in my laptop. Let me open the slide. Setting system. Inside the module. Okay, I started this slide here. Let me show you that what you need to learn for process synchronization. At first, in your last class I gave you some basic idea why how you in which cases you need the process synchronization. You know that I draw one picture like this way, that when there are a few in many instances, not few instances actually, in many instances, a process need to communicate with another process. Also, you know, this is one process block P1, and this is another process is P2. Also, if you think about this memory, let's say here is process P1, here is process P2. Also, you know, this is the two process control block. You know, this process cannot directly access any data from process P1. Also, process P1 cannot directly access the data from this process P2. So how a process can communicate with each other? Communicate actually nothing but means the exchange data. Okay, okay, to exchange data to one process to another process. How a process can exchange data between one process to another process? It can do by using a shared memory concept. Okay, I mentioned in our last class shared memory. Okay, shared memory. So one process P1 at first, let's say process P1 write some data in here, and from this memory, also process P2 read the data. from this shared memory. This shared memory, both process can access, process P1 as well as the process P2, both can access the shared memory. Okay, by using this shared memory, a process can communicate with each other. Okay, this is the first concept. And second thing you need to know that in what is the problem for using shared memory. Okay, what is the problem for shared memory? Okay, so at first you know, I also yeah, probably I showed you this example as well, that let's say process P1, let's say process P1 is nothing but it will execute the code segment. Let's say 1, 2, and 3 code segment it will execute. But in this third code, in this third line of code, what process P1 will do? Process P1 will set a value, and this value will be actually stored in shared memory. Okay, let's say process P2 needs the data. Process P2 actually, let's say, consider, let's assume that process P2 needs to calculate A equal B into C. Okay, this value B will be come from this process P1. This process P1, this value you will get from this process P1. Initially, the value of process B, let's say B is 0. Initially, some process here, process B is 0, value B is 0. But after executing this after executing this line, let's say process P1 P1 B value will be set as 10. Okay, will 10, and this 10 value will be right in shared memory. So B will be the 10, and this 10 will use in here 10 into, let's say, C is 2. So this 20 will be stored inside the variable A. This is 20 actually exact value. 10 is the actually 10. We can say this 10 is the a perfect value or appropriate value or correct value for B. Okay. Now let's check what's happened in case of shared memory. You know that if process P1 runs completely, then it is fine. B value will be set as 10 at line number 3. B value will be set as 10 and it will be right in here. Okay, so B will be 10. Then process P1 will be P2 will be start running, and it will collect the B value from the shared memory and perform its calculations. But in real time, what's happened? This is this process P1 completes its execution first, then process P2 start running. Means that this is non-preemptive approach. Okay, non-preemptive approach. If process P1 is completes its execution and write value in shared memory, process P2 access from this value shared memory. It is completely okay. There is no conflict, or no there is nothing about the inconsistency. Okay, but in real time scenario is different. You know that every almost every operating system is follow the non-preemptive scheduling, not the preemptive scheduling, not non-preemptive scheduling. Okay, non-preemptive means that this process will run, this process will complete runs, then this process will execute. Okay, but in real time, every operating system follow the preemptive scheduling. Means that in any time a process can be preempted, actually preempted. Okay, preempted. Stop its execution. Okay, let's check this. This process P1 continues its execution at line number before line number 3. Its execution line 1 and 2, and before line number 3, it's actually preempted by the CPU. Then you schedule the process P2. Then you schedule the process P2, and process P2 completes execution. And what's value will process B will get here? Because at line number 3, actually it doesn't execute by the process P1 before actually it's preempted. So so line number 3 doesn't execute for the process P1. So B value actually it cannot change. B value cannot set as a 10. B value still is 0. Then you complete the process P2. Now process P2 gets the B value as a 0. Okay, instead of 10, it will be the 0 into 2. Okay, So this kind of inconsistency may happen in case of use of shared memory. Okay, in case of course, the process will be preempted. So preempted scheduling algorithms we follow. So if you use the shared memory, so this type of problems will be arised. Okay, you need to solve. You will get the some inconsistent result. Okay, you will get some inconsistent result. Okay, let's check this how we can remove this inconsistency. So this is the you can remove it by using some synchronization mechanism. Okay, this is why process synchronization comes in. Okay, we'll learn the different synchronization mechanisms. So before we'll start learning the different synchronization algorithms, we need to know some basic on it, more basic on it. Okay, let's check one example, another example. Let's say you have you have one process called P1 and P2. Okay, P1 and P2. Here is one process. This is computer RAM. Okay, here is P1, process P1. Here is process P2. Okay, process P2. There is two process, and this is nothing but process control block. Okay, PCB. You know the PCB. Already you know this PCB, process control block. Okay, here we have the CPU. This is CPU, and CPU may have many register. Okay, maybe register R1. Let's say another register is R2. Okay, two register. Now let's check. Let's see some high level overview that you want to this process what you want to do, you want to calculate at any given time point how many customers inside a shopping mall. Okay, how many customers inside a shopping mall. Okay, inside a shopping mall. Okay, how many customers for a shopping mall. Okay, customers will count. Okay, let's check this process P1. It has a function called process P1. Actually, what it will do, let's say process P1 is nothing but a code. Its codes what it does, it has several lines of code. Here is one variable called count plus plus. Okay, count plus plus, and then it is fine. Here is other line. So what count plus plus will do, it will whenever a person inside a shopping mall, that it will count, it will increase the count value 1. Okay, it will count whenever a person inside a shopping mall. Okay, and process P2 actually counts that when a process actually it will decrease the count value when a process actually leaving out from this shopping mall. Okay, so let's see, this process contains the f2 function P2. This function contained by process P1, and this is the process for P2. Okay, P2 contains this function. Okay, here it will do this count minus. It will decrease the count value 1. Okay. So now let's check. A person comes to the shopping mall. At first, count is 0. Okay. Before we start this check, let's see some another low level overview for this count plus plus variables, how it works. Okay, how it works. If you know about the assembly programming language, it will be easy to understand. Now let's see. No worries if you do not have any knowledge in assembly code. So let's say this is the programs, and this is a one programs. This is your high level code in C++ or Java or some others machine, any others language, C++, Java, C#. We use this kind of incremental operators. Okay, operators. But but uh, but you know that these programs is compiled by the compiler, and then it creates the assembly code and assembly to machine code. Okay, how actually you can implement this count in a assembly code. Let's check how we implement this count plus plus this function by using assembly code. Okay, let's check from here. This is code. How assembly codes will do? At first, it will a called keyword called load will actually load the count variable to a register let's R1, this register. So count will be loading here, and then it will increase the count value by using, if you write in assembly code, you need to do this kind of instruction. Okay, increase the count, increase the value for register R1, and then you need to store R2, sorry, R1 to count R1, then comma count. Okay, count. Okay, then what it will do here, it is increase, and then it will be stored to the, then it will be stored to, let's say this is shared memory, this is the count variables in here, then it will store inside this count variables. Okay, if it is start from 0, then it will be store increment in here and store in the count value. Okay, this is how a machine learning a assembly codes works. Okay, assembly codes, if you implement this kind of increment in by using machine assembly code, you need to write this kind of instruction. Okay, 3 instruction, but in high level programming language, 1 line is fine. Okay, for machine code, assembly code, you need to write these 3 lines. Okay, assembly. Okay, what is the machine code? Machine code is nothing but it's binary format. Assembly's binary format, 0101. What is the load means? It kind of binary 0101 format. Okay, okay, it's kind of machine code. This machine code, actually machine code, MC machine code, is kind of exact same representation of assembly code, but in binary format. Okay, binary format. Okay, this machine code, actually this is the one instruction that your CPU actually face every time to execute the programs. Okay, okay, so now what I actually write this code in assembly, because to actually actually to give you some more idea about this instruction and how actually a process actually works. Previously, you know that we talk about the lines of a code is a execute by lines of a code. Okay, one instruction we consider the high level programming language code, but even essentially the instruction is nothing but this kind of stuff. Okay, this is the instruction. Okay, when you compile your code, it will be assembly code, and then turn it to machine code. Okay, assembly code is, this line is kind of, we consider this is the one instruction. This instruction is faced by a CPU. Whenever you write a program, compile it, it will create the assembly code and then convert it to the machine code. Okay, so machine code is nothing but same line, but it's binary format. Okay, actually CPU is for take the instruction is from the 0 format, but for understanding, now it is exactly same. For understanding, you can say this is code is one instruction. Okay, here is total 3 lines for increment. Okay, for 3, if you write in count plus plus, it will be turned to this kind of 3 lines when you compile your code. Okay, this is line 1, this is line 1, this is 2, this is line 3. Okay, okay, so this is the instruction. Okay, this is called the instruction. This instruction will face by the computer. Okay, this is the difference between program line as well as the computer instruction that we actually we study in our previous class, that we complete your CPU always face the instruction. Instruction is nothing but this kind of stuff. Assembly line, one assembly line is one instruction. Okay, similar thing you can also represent in here for count minus minus. If it is F2, then F2 function, of course there is some line, and then first time what it will do, load count value in different register R2, 1 R2, and then decrement DECR, decrement from this R2 register, and then store this R2 into the count variables. Okay, count variables. Okay, these are the 3 lines you need to write. Actually, you need to write for in assembly codes, or when you compile it, this count minus minus actually converted to these 3 lines. Okay, this type of 3 lines. Okay, and then some others code. Okay, okay. So this is line 1, this is 2, this is 3. Okay, So here is R2. R2 actually receives this count, okay? Count decrement, okay? Decrement the count value by using the R2, okay? Now let's see that you already know that when a programs. Now let's check this how it works. Let's check this now. Currently in a shopping mall, there is count. Let's say 5 person is inside this count inside the shopping mall. Count value is currently 5. Okay, let's check this way. Okay, count is currently 5. Okay, means that 5 people already inside the shopping mall. Okay, now 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 let's see when you run this program for F1 when you run this programs. So what's it will do? It will let's say process P1 is executing the first. So process P1 nothing but this function. So we are considering we didn't consider these things. We consider only the count this instruction. Okay, these are kind of others programs, others line. Okay, here is some others line. We will focus on the count plus plus. Okay, let's say one person is inside, actually comes to the shopping mall now, actually enter to the shopping mall now you check. Okay, you check this value. Let's say load one is count is r count r1 count actually load count value to r1. So count value is 5. Count value is 5. So 5 is load in here. 5 is load in here. Okay, 5 is load in here. Then in this line increment the r1. So this value will be the 6. And third line is store this r1 to count. So this variable will be 6. Okay, 6. Okay, 6. Then it's fine. Okay, now let's check this. One person now out from this comes out from the shopping mall. Then what's happened? Now count is 6. Count is 6. Now one person out from the shopping mall. Let's check this load in this place. Now I am talking about in here. Okay, decrement this decrement operation. Okay, one person out from the shopping mall. So load count to R2. Okay, R2 is nothing but 6. Currently 6. 6 is load in here. Then decrement R2. R2 will be 5. And then store R2 to count. Okay, R2 to count means that it will be stored here 5. Okay, 5. It's completely okay. Okay, one person actually entered to the shopping mall. It increased the count 5 to 6, and then one person also leave from this shopping mall the shopping mall. Then again it decrease the value count value, and its final value is 5. This is completely perfect. Okay. Now let's check in different way. Okay, let's check what's the problems for different sequence of execution. Okay, let me check in different sequence of execution that how it works. Okay, now let's check this let's check this one way that your process P1 executes the line. Okay, let me show you different example. Yeah. Let's say your process P1, I'm considering this process. This is process P1. This is process P1. Okay, this is process P1. Sorry, this is process P1. Let me change the color. Okay, this is process. Okay, here is the process P1. Okay, P1 and its corresponding assembly code. Okay, I am talking about this in here. Okay, process P1 and its assembly code here. This point. Okay, this point. Okay, in different sequence. This line. Okay, 1 to 3 lines. Okay, these 3 lines. Also in this is process P2. Its instruction, and we'll talk about this these 3 lines. Okay, in here 1 2 3 1 2 and 3. Okay, these 3 lines. Okay. Okay, for let's say at first when this process P2 P1 is scheduled by the CPU, P1, and P1 executes the line number. Let's check this. One person comes to the shopping mall, and one person out from the shopping mall. That how it works. Okay. Let's say one person comes into the shopping mall and then out from the shopping mall. So it should be 5. Okay, because count is now currently 5, means that 5% already inside the shopping mall. Now check one person comes into the shopping mall and so one person out from the shopping mall. This count value should be 5. Okay. Also you see that when this process completes this sequence 1 to 3 and this process complete the sequence 1 to 3 this way, it was perfectly fine. Okay, it was count remains the 5. Okay, once comes and another outs. Okay, the shared memory count also was the variable 5. Okay, now let's consider some other sequence. Okay, let's say process P1 execute the line 1. Line 1 means that what it will do, it will load the count value to register R1. Okay, count value to register R1. Count value is currently is 5. 5. So 5 will be stored in R1. Then P1 is preempted by the CPU, and P2 actually executes the line number 1. This line. Okay, this line. What P2 will do? P2 will load the count value to R2 register. Count value is currently 5. So count value will be stored in here by the P2 as well. P2 will load this count value is 5 in here. Then also P2 also preempted by the CPU. Then P1 executes the line number 2 and line number 3. Okay, this line increment line number 2 and store the value. Okay, now increment this R1, so this value will be 6 and this 6 will be stored in here. Okay, 6 in stored in here, shared memory. After executing the P1 execute line number 2 and 3, so this 6 will be stored in here. 6 will be stored in here, shared memory. Okay, now process P1 is preempted and then P2 gets the CPU. Now CPU P2 will execute this next 2 lines. Here is decrement and store. Okay, these 2 lines. Okay, decrement and store. Okay, 2 and 3 lines. So what it will do? It will decrement the R2 value. R2 will decrement this 4 and it will store this R2 to count. So 4 will be replaced by the 6. It will be the 4. Okay. Now let's see that one person in, one person out. It should be the 4. It should be the 5. It should be 5, but it becomes 4. Okay, due to the preemption or different sequence of execution. Okay. Do you get this point, or do you have any confusion, or do you have any questions so far? Okay, let's check another sequence of execution, how it works. Okay. Okay, let me clear some part in here. This is good in here. This is good. Okay. Let's check another sequence. Let's see process P1 and P2 execute this. We are focusing on. I mentioned we are focusing on in here process P1 and this 3 line. This line number 1. This is 2. This is 3. Okay. Here also this is line number 1. This is, we consider this 2 line. This is line 3. Okay, line 3. These 3 lines. Okay. Okay. Now let's check. Let's check another sequence. Another sequence is process P1 executes line 1 and line 2 first. Okay, line 1 and line 2. This line and this line. Load count R1 and then increment the count value. Okay. Now let's check this how it goes. Okay. Let's say process P1 gets the CPU and its executes the 1 and 2 line from there. And here what it will do, load the count value. Let's say 5 in here is 5. Okay, load the count value 5 in here, and then next line will increment the count value R, so 5 will be the 6. Okay, in second line. First line, here is the first line. First line, it's load the count value is nothing but 5 to R1 register, and then increment this count value by 1, means that 6. Okay, after this 2 line of code. Okay, execution of 2-line code, these 2 lines of code. Okay, next, let's see P2 process P2 executes the line, all line. Process P1 now P2 gets the CPU, it executes all these 3 lines. Okay, 1, 2, and 3, these 3 lines. Then after executing these 3 lines, what's actually you will get? You at first you load the count to R2. Here is count is 6, 5. Okay, now load your load count value to R2 is nothing but 5. Then you decrement the count value in second line. Decrement the count value by 1, so it will be 5 to 4. And then you store this R2 value. You store this R2 value to the count in here. So 4 will be stored in here now. 4 will be stored in here. 4 will be stored in here. Shared memory count variables. And then it's done. So process P2 again gets the CPU. Now P1 gets the CPU. P2 is done, and P2 will store the next line, line number 3. Okay, line number 3. P2 will executes. P1 will execute. So P1 will execute the line number 3 because previously it executes only line 1 and 2. Okay, now it will execute the line number 3. Okay, line number 3, what it will do? It will store the R1 value to count. What is the value for R1 now? R1 is currently hold the value 6. So 6 will be stored in here. 6 will be here. Okay, 1 person in, 1 person out. Instead of 5, you will get the 6. Okay, so before you also get the 4 as well. Okay, so due to the sequence, or due to the preemption of different processes, you may get the different value for a shared memory or shared variables. Okay, so how you can solve these problems? Okay, now let's see why this problem actually happened. Okay, why this synchronization problem is happened. Okay, sorry, why this mismatch. Okay, mismatch is happened. Okay, so now let's check your code. Okay, now let's check your code. Actually, the inside your code, the place where actually a process needs to access the data from the shared memory. Also here, this is the code segment. Let's say this is the code segment for this process P1. Here actually this process needs to access the value in shared memory. Also in here, this is the code segment or code block. The process P2 needs to access the value from shared memory. Okay, this is this code segment. Okay, this code segment. Okay, also you know that when this process is complete, this sequence is done, and so this sequence is done without any preemption, then there is no problems. Okay, so when a process needs to access the shared memory inside a code, this code is nothing but the critical section. Okay, so here we figure out what is the critical section. Okay, critical section is nothing but a process code a process code need shared memory is actually process code needs to access the shared memory is called the critical sections of your code. Here this is the critical section. Here this is the critical section. In this section of code, your process needs to access the shared memory. Okay, this is critical sections, and others code actually if it doesn't require to access the value from shared memory, this is the non-critical section. Okay, here you will get two things. One is the critical section, another is non-critical section. Critical section is simply written as a CS, and non-critical section will write as a NCS, non-critical section. Okay, so when your process need to access some value from the shared memory, there should be some code in a there should be some critical section. Okay, of course, some other part is fine. It is non-critical section, but your process or your programs needs to identify the critical sections for your applications or for your software, for your code. Okay, critical section. Okay, so now you get the idea why this is the critical section and which part is considered as a non-critical section. Okay, critical section is nothing but when the pieces of code that needs to access the shared memory, and non-critical section, the process that needn't actually access the shared memory, is known as the non-critical section, or other critical, and rest of the code is considered as the non-critical section. Okay. Also, one thing it is clear that depending on this order of execution, you will get the shared value is different. Okay, I showed you that if it's completed, if P1 completes its execution without any get any preemption, and then P2 completes its execution without getting any preemption, then it is fine. You will get the in and out 5. Okay. Now, due to some sequence of execution, you get the count value 4, and again there is another example I showed you. You get the count value as a 6. Okay. So due to the depending on the order of execution of code, you may get the different result for a shared value or some inconsistent result. Okay, this nothing but the inconsistent result, that is called the race condition. Okay, so two new things you get here, 2 or 3 new things. One is critical section, non-critical section, and another is race condition. Okay, race condition. Okay, race condition. Okay, let me clear in here. Clear some part in here from here. So this is we learn the what is the race condition. Okay, condition. Race condition is nothing but depending. It is actually known as a depending on order of execution of code. You may get the different result. Is called the race condition. Okay, so race condition occurs both process enters or execute the critical section at the same time. Okay, this is very important point. Okay, this is critical section. Also, here is one is that one is also critical section. Okay, let me change my color again, then you can get. Okay, this is the critical section part. Also, this is one critical section for a process. Okay, what's happened? If both process enter into the critical section at the same times, that is the problem. Okay, that's time race condition occurred. You will get the inconsistent result. Okay, you will get the inconsistent result. Okay, you identify the critical section, and you need to ensure that when a process inside the critical section, then another process shouldn't be inside this critical section. You have to actually ensure this condition. That time you will get here consistent result. Okay, if actually two process, if two processes has some critical section, and both processes actually allow to access this critical section in the same times, then you will get the inconsistent result. Okay, actually you need to ensure that there is not more than one process inside the critical section, then you can avoid the race condition as well as the inconsistency problems for the shared memory. Okay, now we need to actually figure out that how we can actually control these things. Okay, how we can control this race condition, how we can control the if one process inside this critical section, how we can prevent to other process don't enter the critical section. Okay, this thing you can done by using different synchronization mechanism. Okay, okay, and another thing is that perfectly true that that if a process inside this critical section, if a process inside this critical section, then other process can execute the non-critical section. It is completely fine. Okay, it is completely fine. Okay, these things you need to know that understand that the both process cannot actually execute the critical section at the same time. Okay, but this process executes the critical section, but this process executes currently non-critical section. This is completely fine. Okay, your computer can do this. Okay, it is allowed. Okay, but now let's check actually the thing that I mentioned. It is like this: if this process p, let's say process p1 and p2, if p2 is in let's say this is critical section, this is non-critical section, process p2 is in non-critical section, this is cs and cs and cs, and let's say this is cs and cs. This is combination, some combination, this combination can be happened. Okay, okay, here is process P1 in critical section and P2 is non-critical section. This is completely fine. Here process P1 is critical section, process P2 is also critical section. This is, you cannot do this. Okay, you cannot do this, execute this type of this type. Okay, but non-critical and non-critical, both processes non-critical section, it is fine. Process P1 is non-critical, process P2 is critical, so it is also fine. Okay, so only this situation you need to avoid. Okay, okay, to ensure the consistency for your code. Okay, for your code. Okay, now let's check one more things. So now you will get some idea that what is the critical section, what is non-critical section, what is the race condition, and critical and non-critical execution is fine, but critical section and critical section is execution is problems. You need to check this kind of section. Okay, now how we can check these things, let's explore a bit. There is process p1, here is also one process p2. Let's say there is several instruction line, 1 2 3 instruction, this is instruction. Okay, 4 5 6 7 8. Okay, also process p2 contains 1 instruction, 2 3 4 5 6 7 8. Okay, this kind of stuff. Okay, now let's check, let's consider this two line is non-critical section for this process, and this two lines is critical section for this process, and this all of this block is non-critical section. Okay, here let's say let's check this three line is non-critical section, this two line is critical, here is this three line again, this is the non-critical section. Okay, for your programs. Okay, now how you can actually prevent these two two process shouldn't be inside this critical section at the same time. Okay, you need to ensure this. Okay, now how you can do this? Okay, let's take one real-time example. Let's say here is nothing but critical section. Let's consider this is one row. Also, here is also one row. There is also, this is non-critical section, one row. This is critical section, is a one row. Here is also one row. Okay, it's kind of like this. Here is also, this is non-critical, this is critical, this is critical. Okay, this is nothing but two rooms. Let's say two rooms. Okay, or two house. Okay, you need to ensure that two house cannot accommodate at the same time. Cannot house accommodate at the same time. If a person inside the house one, there won't be any person inside the house two. This is S1, this is S2. Okay, if a person already inside the house S1, then it if another person come, it shouldn't entry for this house H2, okay, like this. Or inversely, you can say if a person already inside his house 2, and if another person comes in, it shouldn't allow to enter this house H1, okay, H1. So how we can do this? Let's say here you have a guard or watcher. What's it will do? It will do here. It's kind of it's contain one ticket, okay, ticket or key, anything. So, okay, key. Once a person also this key, let's say, works for these 2 houses, okay, 2 houses is fine, okay. Okay, so if a new person comes on the single person, then comes and it will take this key and enter this house, okay, and then a token, we can see this token. And so now there is no token for this person, and then if again new person comes, there is no token for this. So this person will not be allowed to enter this house too. Once this person comes out from this house, it will return the token to this man, and then this person is allowed to go enter this house, okay. This kind of approach here you can also apply for entering the critical section as well, okay. How you can do, we don't have the person or kind of like this, but we have some code, okay. We can write some code in here before, add some code block before critical section, okay. Before this is the critical section, so you need to add a small piece of code. This is, let's say, also here also you need can add a small piece of code, a small piece of code. This is known as the entry section, okay. Entry, okay, entry section for critical section, okay, for a critical section. This is entry section, and also this is the entry section for this critical section. This is also simple, same code, entry section code. Also here also you need to add some lines of code for exit section, okay. This is exit section, okay. Also here also after this critical section, then you need to add some code for exit section as well, okay. Exit section, here is also entry section. This is entry section, okay. These 2 things you need to add, okay. One is for entry, another is for exit section, okay. Now what it will do, what this entry and exit section will do, entry section will check if this process execute line number 2 and then enter to the critical section, which is line 3 and 4, okay. So this code segment will check whether this process is already entered the critical section or not, okay. If it is not, then it will allow to this process enter the critical section. Otherwise this process will actually stop in this location, okay, stuck in this location, okay. How can do this? You can make a while loop in here, infinite while loop, okay. You just keep looping in this section, okay. Also, and then always it check, okay, whether wait for this, if this process comes out from this critical section, what its exit, then this process should allow to go, this entry section should allow to go this process to the critical section. And once this process comes out, then exit section, what it will do, it will actually ensure that this process is completes its execution to the critical section, okay. This exit section code will reflect these things, okay. This process P1 completes its critical section, execution of critical section, then this process will be allowed to go enter the critical section, okay. This is how you can actually manage the who will enter the critical section, okay. This managing thing is called the synchronization mechanism, okay. There are different synchronization mechanism you can apply to enter a process inside the critical section, okay. There is different kind of algorithm, okay, mechanism. We'll learn one by one. Synchronization mechanism, okay. Now let's see that how how you can actually ensure that which synchronization mechanism actually works better than the other synchronization mechanism. Okay, how you can check? Okay, perform this actually evaluation that which synchronization mechanism is better than the other synchronization mechanism. Okay, how we can do this? There are three three methods or three evaluation criteria that actually ensure that which synchronization method is better than the other methods. Okay, other synchronization methods. Okay, there is first one is, okay, let me clear some part before I explain this synchronization mechanism and how you can evaluate a synchronization mechanism. Okay, there are several synchronization mechanism we will learn one by one, but now check which basis you will consider that this synchronization mechanism is better and this is actually not good as this synchronization mechanism. Okay, how we can do this? There is one criteria is called the mutual exclusion. Okay, mutual exclusion. Okay, one criteria is called the mutual exclusion and another thing is called the progress. The third is bounded weighting. Okay, bounded weighting. Bounded weighting. Okay, these three criteria, actually by using these three criteria, you can consider to evaluate a synchronization mechanism. Okay, first let's check what is the mutual exclusion. Okay, what is mutual? What actually mean by the mutual exclusion? Okay, in definition, mutual exclusion is the way of making sure that if one process is executing the critical section, then other process cannot enter the critical section until the executing process comes out of the critical sections. Okay, this should be obvious. Okay, mutual exclusion means that if a process already executing the critical section, okay, then your synchronization mechanism shouldn't, whatever the synchronization algorithms you actually use, your synchronization algorithms doesn't allow another process to enter the critical section. Okay, until the executing process comes out from this critical section. Okay, until let's say this process P1 is now inside this critical section. Okay, so your synchronization mechanism or synchronization algorithm shouldn't never allowed process P2 to enter the critical section until this process P1 comes out from this critical section. Okay, this is very important criteria. Okay, if it is mutual exclusion actually violates, means that your synchronization algorithm actually mechanism doesn't work. Okay, I give you this criteria because you will see that some synchronization mechanism doesn't follow the mutual exclusion. Okay, at a time two process can inside the critical section. Okay, so this is very fast and big criteria to actually maintain the synchronization. Okay, to fulfill the fulfill the consistency. Okay, this is very important parameters. If two process inside this critical section, then mutual condition is violated. Okay, if two process inside this critical section, that it actually doesn't make any sense for the good synchronization mechanism. Okay, then next is the progress. What is the progress? Progress actually is the way of making sure that if a process is not inside the critical section, then it will not block other processes from the entering the critical section. It is progress means that let's say this process P1 is not inside this critical section, that time this process P1 actually shouldn't block this process P2 for entering the critical section. Okay, this is also obvious. It is called the progress. Okay, if this process is not inside this critical section, so this process shouldn't actually shouldn't block this process P2 for entering the critical section. Okay, this is called the progress. Okay, we will see that some process actually violate this progress rules as well. Okay, how it works? It will, let's say process P1 is not inside this critical section, but still this process will not allow to entering the process P2 inside this critical section. Okay, so progress property will be violate some processes as well. Okay. So far, do you have any questions or comments regarding process synchronization? Okay, we today we learn a couple of things. Yeah, some concept, really some important concept for understanding the process synchronization. One is critical section, one is non-critical sections, as well as we learn the race condition. This is very important concept, race condition, and then how we can some actually high level overview for synchronization mechanism. So we need to add a entry section as well as the exit section for entering a process to critical section. Okay. Okay, and then we learn the how we can evaluate a process, how we can actually evaluate a synchronization mechanism. Okay, there are three criteria. Criteria is called the mutual exclusion, progress, and bounded conditions. So we learn bounded condition and progress. If some process fulfill the mutual condition, mutual exclusion and bounded conditions, but not fulfill the progress, then it is not a good synchronization mechanism. You see some process, some synchronization algorithms fulfill the, it doesn't fulfill the mutual exclusion, only fulfill this progress, and also doesn't fulfill the bounded waiting as well. Okay, so this is also not a good synchronization algorithm. Good synchronization algorithms means that it should follow this all, or it should actually fulfill this all three criteria. Okay, all three criteria. Okay, so our next criteria is the bounded condition. Okay, bounded waiting. Okay, what is the bounded waiting? Okay, a way of it is a way of making sure that there is no exit bound or time limit on the number of times other processes are allowed to enter the critical section after the process has made the request to enter the critical section. Okay, this is little bit tricky, so you need to understand clearly. So this part is little bit tricky. Okay, today we are almost running out time. Okay, so do you have any questions or comment before we go? Okay, so if you do not have any questions, we can stop here today. In our next class, I'll show you that what is the bounded conditions and how it works. Okay. Okay, so have a great break. Okay, we'll see. Okay, we'll meet again after the spring break. Okay, have a great break. Okay, thank you everybody.